All right, hello everyone. I wanted to do just a quick review of the square planar versus tetrahedral geometries that we talked about at the end of lecture today, just to make sure everyone feels comfortable with that. So I wanted to first go over how we came up with the square planar geometry. So I'll use the example that we had in class with platinum, cisplatin. So if we draw our cisplatin formula, we know that we have two amine ligands, two chloroligands, platinum 2, which makes this a neutral complex because chlorides each have -1 charge. So if this were to form a tetrahedral geometry, we just learned that we would get a d orbital splitting pattern that looks like this, where we have the dz squared dx squared minus y squared lower in energy, dxy, dxz, and dyz higher in energy. And so if we have platinum 2, of course we know that platinum 2 plus is a D8 complex. So let's put in our 8 electrons. Looks something like that. Okay. Now, if we draw the square planar geometry, we said in class that we can take a octahedral geometry. So let's just say we have two ligands on the axial plane of the platinum above and below the square plane. So of course, if we had square planar, we would have that orbital splitting. Where now the dz squared and dx squared minus y squared are higher in energy. And we said what we can do is we can just remove those ligands from the z-axis. Remember, this is our z-axis that goes up and down through the molecule. So if we remove those ligands, we've removed electron density from the z-axis. So then any orbitals that contain z character, right? So remember, if they contain z character, that means they point in the direction of the z-axis. So if we're removing ligands from the z-axis, these three orbitals ought to go down in energy or be lower in energy relative to their counterparts. So let's now redraw this in the square planar geometry. We've removed those ligands from above and below. And now we're saying that we're going to then have less repulsion on z-axis orbitals. So those ought to then have lower potential energy. So the dxz and the dyz would go down. This dxy would be slightly higher in energy. And then same thing here. Now the dz squared would be slightly lower in energy than the dx squared minus y squared. So we've lowered the potential energy of the three orbitals that have z character because we've removed a lot of electron density from that z-axis. Okay. Now again, if we have d8, now we're going to fill the lowest energy orbitals first. It turns out all of the energies of these square planar orbitals are large enough, they're different enough in energy to where we're going to fill up the orbitals first before we go to the next highest orbital. So we get paired electrons in each orbital. All right, so here's our square planar geometry in our electron configuration compared to tetrahedral. So what I tried to explain in class, I apologize if this wasn't clear, but essentially what we are going to do now is we're going to compare, and actually let's pretend this is tetrahedral. And so remember, now our angles here are 109, our angles here are 90. Okay, so in order to favor this square planar, we have an increase in potential energy. So we're making the angle closer. We're pushing these ligands a little bit together. Remember, there's electron density in those bonds. So that's going to be a higher potential energy, less stable. But the driving force for that is that if we look at these orbitals, this is an unequal distribution. Meaning we have 3 orbitals of the same energy that don't look the same. So you have different numbers of electrons in equal energy orbitals. It turns out in nature that having, so if we had 3 sets of paired electrons or 3 unpaired electrons in these top 3 orbitals, that would be more stable. So it just turns out that nature likes to have an equal distribution of electrons in degenerate orbitals or orbitals with the same energy. It just happens to be a lower potential energy state. So here we can see we have an unequal distribution. So this is going to be higher potential energy. Here in our square planar, we have a perfectly equal distribution of electrons. That's going to be lower potential energy. All right, so with D8, so when we have a D8 complex, going into this square planar geometry is actually more favorable because of the electron distribution. So even though we have a higher potential energy from the smaller angle, we get a lower potential energy from the electron configuration. It just turns out that in nature, this is going to be a little bit more stabilizing than trying to go into a tetrahedral geometry. So D8 are really unusual. They're just about the only time you'll see 4 coordinate complexes go into this square planar geometry. Okay, so I hope that helps clarify a little bit why the square planar is more stable for D8. And then we ended the class with this example where we had a D7 configuration. So let's look at these now just to review. So if we have tetrahedral, and let's just say we have a metal with 4 ligands. We again know that that's about 109 degrees. And if we have 7 electrons, we would look like that. And then if it's square planar, right, of course we know that we have the metal, with 4 ligands, but now in the 90-degree planar geometry, it would look like this. Let's put in 7 electrons. Now we can see in this case, not only do we have a lower potential energy bond angle, we've got less repulsion between the angles, but we now also have a perfectly equal distribution of electrons, which is also lower potential energy. So for D7, there's no driving force to go away from the tetrahedral, because not only do we have a better bond angle, but we also have a better electron distribution. Whereas over here, we can see that we have a higher potential energy again with this smaller bond angle, and we have a more unequal distribution of electrons, which is generally going to be a higher potential energy. So DH is a really unique case. It has just the right number of electrons to where if it goes square planar, it gets a better electron configuration versus if it goes tetrahedral. And so that's what I was trying to show you with this example at the end of class. So I hope that clarifies the discussion of square planar and tetrahedral. And then we just want to end with then our discussion of cisplatin. So we talked about earlier in the quarter when we did equilibrium how cisplatin can form these interactions with DNA. Well, now we know how coordinate covalent bonds form. So if we look more closely at that picture, we could see then that if the cisplatin loses chloride, so if it can lose a chloride ligand, which we know can occur due to the Le Chatelier's principle, and then when this gets into the nucleus, it can now bond with the DNA. So here we have our guanine base pairs, and we know that this would have a lone pair here, lone pair there, so that we could form a coordinate covalent bond with platinum. And so what can happen then is you can get two different forms of interaction. So you can get this intrastrand, so where two guanines that are side by side would then both bond to the platinum, or the interstrand, where now we have guanines from opposite sides of the DNA helix now bonding to the platinum. Now, generally speaking, both would disrupt DNA replication. And so generally that's how cisplatin is able to kill tumor cells, because if the DNA can't replicate, cells can't divide. But you can see here that it turns out that DNA repair that can take place in the tumors will tend to work more efficiently if you get this intrastrand crosslink. So if you get these more intrastrand crosslinks with their cisplatin drug, it tends to be a little bit less likely to form resistance. The tumors are less likely to form resistance. So at any rate, just wanted to kind of throw that in there to wrap up that discussion of square planar and tetrahedral. So it turns out that cisplatin being square planar and not tetrahedral allows it to form these types of interactions with DNA much more efficiently. So the fact that cisplatin is square planar just gives it these certain properties where it's able to form these types of interactions. So hopefully that helps you then kind of wrap up where we started with the chapter when we talked about why was gold 3 and platinum 2 both square planar. Now you know why. It's due to this D8 configuration. And again, just to remind you that the applications of these metals can be quite important, even in terms of medicinal chemistry, and in particular with this chemotherapy application. All right, so I'm going to stop there. I am going to do one more wrap-up video to give you a couple more examples of coordination complexes and the applications that they can have. So you can start that after you end this video. All right, talk to you soon.